And wrapping up this session is the presentation by Stanislav Moiseev, the head of the team developing algorithms for big data analysis, Moscow office, Huawei. ARM processors today are becoming more and more popular. And Stanislav is going to tell us about the optimization of machine learning algorithms using ARM processors. You have the floor. Good afternoon, everyone, and thank you for the kind introduction. My name is Stanislav Moiseev from Huawei, Moscow Research Center, Big Data and Data Science. Now, I will tell you more about our algorithms development for big data analysis. It's a short presentation, I only have 15 minutes. Our company uses a whole stack of technologies on data analysis. Our approach is to supply the customers with not separate components, but however complex, comprehensive solutions, beginning with hardware, servers, chips, other accelerators, and ending with separate algorithms which allow our customers to quickly tackle their jobs. Our framework in data analysis is called Kunpeng Boost Kit for Big Data. Consists of hardware, platform, operating system, middleware, and big data computing frameworks. Supported big data platforms include Huawei, Fashion Insight, open source Apache platform. Now, let me go into Huawei Kunpeng 920 processors. That's the name of our chip, ARM-based, up to 64 CPU cores. Various options, desktop cards using dual chip architecture up to 128 CPU cores, and we are also producing service cluster supercomputers. We do it all. However, today the story is about big data algorithms. And here we have taken Apache Spark. At least in our project we use Apache Spark streaming, and we think that Spark had long proved to be mainstream technology for big data analysis. Many customers use Apache Spark. Accordingly, Huawei here focuses on the machine learning libraries and graph analysis algorithms analytics. We would like to improve it, develop it, and of course make them more usable. Now, why is this interesting? Why did we select this vector? We had selected Spark. We looked at MLlib and GraphX, open source solutions for graph analytics and classic ML, but we disliked it for some reasons. You'll probably ask why we're not using standard open source solutions. Look, we have detailed two key problems. These libraries are lacking very important algorithms required by our customers and us. This has to do with graph analytics. GraphX only uses less than 10 algorithms, and many important algorithms are simply missing. We did a POC solution with one of our customers who needed to detect community, and we did an algorithms of maximum click algorithm. However, there was no such algorithm, and we had to develop it independently. Another problem is also limited algorithm generalization and incomplete coverage. Algorithms may support only certain size data, for instance, singular dispersion and PCA and SVD decomposition algorithms are supported by Spark. They're open source. However, they only support for dense data. And if we want to use it with sparse data, we will see serious limitations in terms of scale regarding maximum size data we're able to process. We'd like to accordingly resolve these tasks. We'd like to expand our graph and MLL graph library, which is what we're doing. The project was launched over around 2 years ago, and today we see some progress. We aim to present our own version of Spark ML and GraphX libraries, however, quicker, faster, and more powerful. We are promising our clients that we guarantee 1.5 time acceleration when using our computing capacity. However, in real life, compared benchmark against best open source decisions, we achieve much higher acceleration. Also, we guarantee that our IP is completely compatible with standard GraphX and Spark algorithms. For this reason, the customers won't need to specifically restructure their scripts and pipelines. Our algorithms will suffice just the change in jar file, and everything will work well quickly instead of standard open source solutions. Now on this slide you see some information on our results. This is a list of algorithms that were already part of the release and were publicly announced and launched. This group decomposition, graph decomposition, SVD, OQR, and others, ensemble method of ML, pastization against graphs, communities, centrality, decomposition matrix, and all of the other standard algorithms. 67% improvement to 2,500% improvement. It provides for increasing speed and acceleration of our algorithms benchmarked on standard data sets against open source solutions. Let me give you a few cases of our solutions to illustrate, to demonstrate our work. Gradient boosting was already mentioned today. Very popular algorithm, machine learning, proposed in 1997, very good for analyzing structured data and even overtaking the neural nets in place in terms of speed of learning. The idea is quite simple. This is an ensemble method which is learned through adding weaker models, and as a rule, the decision trees are used as weak learners, CBT algorithms. Others are also possible. However, gradient boosting is usually viewed across decision trees, and of course, construction of optimal decision trees is an NP-hard problem. There is a formal mathematical theorem on this. So at the moment, there are no fast algorithms known that would provide optimal solution, and they cannot exist in real life. We use the ensemble models where a large number of trees are learned, and the sum total weight is done through individual tree weights. And gradient boosting is very popular, used in many industries, Rexis, credit scoring, and also in the big collider. It was also used. There are many various solutions openly available: GBoost, GBM, and GBDT algorithms for Spark. So we decided to also invest into this development and make some steps to develop this algorithm and probably our own libraries of boosting algorithms. So we had taken XitBoost and version for Spark and had endeavored to improve that. Our approach is to preserve the user interface because we promised users we are not going to change the interfaces of open source solutions, so we don't change the semantics of existing functions. However, we add our own parameters. Every parameter in this case is responsible for separate setting, optimization, tuning. It may be the fine-tuning of the actual algorithm or a mathematical feature. It also may be a setting that optimizes data transfer protocol, providing for different configuration clusters, optimized calculation time. In any way, we provide the customer with an API, and here are some cases of test outcomes where we had taken standard regional AIJ boost, optimal configuration, by 8.6 cluster, and also Huawei cluster, and also our optimized AIJ boost for dispersed scenario. As you see, we were able to improve speed almost double. Using Huawei ARM server certainly is faster compared to x86 architecture. And a lot of attention is given to mathematics, algorithms, sorting, calculation models. In our team, quite often we come up with new methods and algorithms that are not described in the articles or not fully presented in the literature. One of such achievements is our DB-scan algorithm. It's a density-based non-parametric clustering algorithms for spatial clustering of applications with noise based on density, and it also finds outliers, detects, identifies marks outlier points that lie in low density regions. As we learned, sparse environment don't have good DB-scan solutions, and those solutions we located work too long at best and cannot cut longer scenarios. So that's why we had to develop our own algorithms, our own clustering algorithms, our own solution combining few mathematical models. We came up with a solution that uses time codes, tree codes for clustering in low density regions, and then uses local DB-scan, where we had taken the distributed algorithm design on one machine parallel, and this combination turned out to be the most optimal, providing this 50-fold acceleration on some data set. The larger the data set, the more gain we saw benchmarked against best open source solutions. Now let me give you a few cases from graph analytics. Now the centrality measure is a very popular measure and even class of measures in the graph theory. Now there are many various definitions of important top given node. One of them is that's a graph characteristic. Betweenness centrality is a graph characteristic which indicates the importance of a given node in terms of how often it serves as a connection between other nodes in the network. The more other nodes depend on it to make connections with each other, the more important the node is. You can see the mathematical formula on the left of the screen. So this is quite a popular matrix used in many industries, for instance, telecommunication systems. Its centrality presents the nodes that are very important for transfer information. If there is a problem in one node, this can affect the workings of the whole chain, of the whole network. In the social media, high centrality corresponds to the influential community members, those quickly generating information, opinion leaders, and identification of these graphs, of these graph tops is also very important for social media analysis. Now, what is the challenge and the problem? The problem is that this is a very extensive calculation challenge. We have tested the exact method of calculation centrality using the road grid plan. This was a plain graph, 24 million tops, 29 million edges, weight graphs, 24 million nodes. We used 30 service, 96 core per server, totally 28 80 cores for a road network. And in one of our in this experiment, the exact computation took to calculate between centralities took us over 10 days. So in practice, we are using between algorithms. But what is the pitfall here? Approximation is difficult as minor changes in the graph may cause significant centrality changes because it's not a local characteristic. And small changes in the graph in a certain point can lead to the structure of the shortest pathways will change. And so the meaning of centrality in another section of the graph may drastically change. So accordingly, overall structure is important, and we use sample method. Accordingly, we did the analysis on a large number of strategies and came up with adaptive sampling strategy, which works better than others. We'd like to present the results of our experiments. Bottom line corresponds to data set I mentioned earlier, where we calculated the precise values over 10 days. We were able to achieve 93% accuracy for 10,000 tops out of 10 million. The graph edges were located in under an hour on a cluster of less than 3 machines. We think it's quite a good acceleration accordingly. And this algorithm is used also by one of our clients.
And to conclude, I would like to say a couple of words about our tech stack. Technological stack consists of 3 levels. First level, the top level, is the algorithms level, where we develop new methods of machine learning or graph analytics, clusterization of detected communities, and so on. Next level is operators level. That's where we implement general mathematic operators, for instance, optimization solvers of levels 1 and 2, matrix methods, or other approaches. So these are general things for many algorithms, and they should be developed separately. And on the lowest level, we have low-level mathematical libraries that are optimized for our ARM chip. And there are standard libraries like Scalapack, Lapack. Their interfaces are standardized, and they can be optimized for specific hardware. That's what we are doing in our company. And my final slide. Approach of our development is shown here in 4 main principles. First, we select the most popular algorithms and implement them. We guarantee acceleration of at least 1.5 times against the best open source solutions. We can guarantee a stable API, and the users will not have to change their code or rewrite it, just to change a couple of files. And we guarantee that using our libraries, users can either buy less amount of equipment or save man-hour while waiting, while algorithms are calculated. So we're open for cooperation and joint development and joint work. Thank you very much for your attention. Thank you very much. Indeed, impressive results. We have time for another question, for one question. Question from our viewers. What is the specificity of analysis of data on architecture? Is there any specificity in implementation of algorithms? We have some specificity in how we optimize algorithms. First of all, at our platform, ARM servers, usually we have more cores than on Intel servers of the same price. That's why we can be stronger in the processes and implement algorithms that can be checked thoroughly. Another thing, there are specificities to the chip, the amount of cache and memory. It can be different from ARM chip and Intel, and we use this knowledge for some internal algorithms. But from the point of view of top level and using the ML, actually, there is no huge difference, and we guarantee the interface of users and the semantics of our methods. Cool, thank you very much. I'm sure that many want to try it now after your presentation. Unfortunately, we have to close our session. It's hard to put into 2 hours everything that happens in this hot topic of recommendations. We tried to select the most interesting themes for you, the most interesting presentations, and I'm sure that all of you, that was interesting for all of you today, but AI Journey is underway now. Thank you very much for joining us and have a good day. Goodbye.